Today I'm going to talk to you about linear regression and correlation. These are both analyses that have some similarities, but also some important differences. And we use each of them when we're looking for linear relationships between two continuous variables. So for example, we'll go back to our discussion of variable types. We'll talk about continuous variables. Those are those measured along a number line versus discrete variables, another type of quantitative variable that's more like a count, right? So those are our two quantitative variables. And compare those to categorical variables like nominal variables, things that are names or words, okay? So to start off with, we're going to talk about four basic types of statistical analyses. The first one you've already seen. This is when you have a categorical X variable and a categorical Y variable, and you're going to use a chi-square test in this example. The next type is when you still have that categorical X variable, but instead you have a continuous Y and you're comparing two means or multiple means. In this case, you're going to use a t-test if you're comparing two means, and you'd use what's called an analysis of variance if you want to compare more than two means, like what's shown there, the 3 bars. Now, today we're moving over to the types of analyses that have continuous Y variables. And you can have a continuous X variable. And so you can have a continuous X variable with a categorical Y variable. And that's a special kind of analysis called logistic regression. We're not going to go into that in this course. But what we're going to focus on today is when we have a continuous X variable and a continuous Y variable. And this kind of analysis, you would produce a scatter plot and you would use either regression or correlation. So what's nice about thinking about the tests in this way is all you have to know is what kind of a variable is X, categorical or continuous, and what kind of a variable is Y, categorical or continuous, and it tells you what kind of a test you should run. So you should never have to ask yourself, what test should I run? Like, there's not really a choice. It depends on what kinds of variables you have. So come back to this slide if you have questions about what test to run in certain circumstances. So when we're looking at linear relationships, we can see a whole variety of relationships. We can see this one here, which shows a positive relationship as X increases, Y increases, and there's some scatter around the line. We could see a negative relationship like this as X increases, Y decreases, and it's a very tight relationship. We could see some kind of a nonlinear response where you get a curve, right? So you can see that the change in Y is actually not constant through time, and it slows down as X increases. You could see a curvilinear response where you have the highest values of Y at intermediate levels of X. You could see literally no response, right? So in plot E here, you can see that there's no linear relationship. It's a flat line. It's like a dead pattern, meaning that as X changes, you don't see any predictable change in Y. And then you could see some scatter around a plot going down in a negative direction. So there's lots of different options here. We're going to focus today on scatter plots. We're going to focus on straight lines. So we're not going to deal with these curvilinear relationships. So here we can see we have linear increasing, positive relationship, a linear decreasing, negative relationship, or some kind of nonlinear relationship. And again, we're going to focus on the linear relationships in this lab. Here's a little joke for you. One guy says to the other, "It's a nonlinear pattern with outliers, but for some reason, I'm very happy with the data." Anyway, hopefully that gives you a little bit of levity. All right, so another thing about linear relationships is that you need more than 2 points to run a regression or correlation analysis because a straight line will always fit 2 points perfectly. So it doesn't really tell us much about change in X and change in Y if there's only 2 points in the data set. So you always need more than 2 points to run a regression or correlation analysis. So how do you choose regression or correlation? Both regression and correlation are used when you have continuous Y and X variables. The distinction has to do with which one is dependent on the other. So if y, the one on the vertical axis, is dependent on x, then you should run a regression analysis. Now, if y is not dependent on x, or if both y and x depend on each other, like if you could easily flip-flop the axes, then you should run a correlation analysis. So some examples would be that sunlight increases plant growth. So if you provide a plant with increasing sunlight, you should see an increase in plant growth. Now, you wouldn't say that plant growth causes an increase in sunlight. So most of the time, you should be able to figure out which variable could be dependent on the other. An example of when two things might be correlated, right, would be like your shoe size and your pant size, right? Like a bigger person would probably have larger pants and larger shoes. And so pant size and shoe size might be correlated. But if I went out and bought bigger shoes, that wouldn't mean that I would need bigger pants, right? So they're not really dependent on one another. They're dependent on genetics or your environment or a G by E interaction. So the first step is always to ask yourself, should I run a regression or should I run a correlation? In some ways, these are similar analyses, but you're making a very different inference and you're asking a very different question. So the only time you should use the word correlation in statistics is when running a correlation analysis. And this is really tricky because the word correlation is used in the US English much more loosely. So I would just ask, in statistics, watch yourself. Try not to use the word correlated or is there a correlation when you're not comparing two continuous variables that are, in a sense, not dependent on each other, or dependent on each other, but not one dependent on the other. So a correlation is, again, a linear association. And you can see a correlation where you have an R equals 0. R is called the correlation coefficient, would just look like a scatter shot, like shotgun shells, right? A correlation like you see in the middle top panel is a negative relationship, but it's pretty weak. It's not very tight. And as that pattern increases, now you see there's more tightness in the top right. So we have an R of 0.5. You see this kind of like band of points moving up. At the bottom, we see an R of negative 0.7, right? Things are tightening up. An R of 0.9 really tight, an R of negative 0.99. Okay, so R can range from -1 to +1. Negative values mean that the pattern is moving, that Y is decreasing as X increases, and positive correlations mean that Y increases as X increases. So Pearson's little r denotes the strength of the correlation, and it can range from -1, a strong, very strong negative relationship, all the way up to +1, a very strong positive relationship. And if you take that R value that's calculated and you square it, you get what's called R squared. And in this case, the R is a lowercase r. And that is it tells us the percentage of the data set, okay, all of the variation in the data that can be explained by the linear association or by the correlation between the two variables. So I want you to take a 10-minute break and come back and watch the next video.